hear me like loud, clear?
Yep.
Perfect. Okay. All right. So today I'm going to talk about graph theory applications for mechanism reduction. And I'm with the McNeil lab at Columbia University. We are technically a chemical engineering lab, but it seems like this field, like people can come from all sorts of different departments. Yeah, my work has centered around focusing on taking large organic mechanisms like the isoprene mechanism, or some other ones I've worked with would be like alpha pinene, or there's some more niche models like camphene, which is big like wildfire byproduct. And the goal is to take these really large models and reduce them into something much smaller to be used in things like geochem or CMAC. And the current mechanisms that are used in those models are very small, but they're usually handmade, which means that there might be some bias in the actual making of them. There might be some theoretical like imperfections, and also they're not adaptable to new information, which means that someone has to go in and make an update, and it usually takes some time. So the goal is to have an algorithm that will reduce the mechanism in a trustworthy and useful way, so that whenever there's an update or whenever you have a large mechanism that you want to reduce, you can. So I'm going to start with just kind of an overview of how graph theory connects to chemical mechanisms. And some of this might be kind of obvious, but then it plays into how the algorithms actually end up working. So here's an example of an abridged isoprene mechanism, or actually the reduced isoprene mechanism, and the graph theoretical representation of it. And there's some certain simplifications I've made to actually make this graph a little simpler, which is whenever there is a atmospheric background species that's reacting with an organic species, we're representing that secondary reactant as a type of the edge in the reaction. And so in representing chemical mechanisms as graphs, usually species are nodes and reactions represent some form of edges. And in this case, I'm just taking the background species out of the nodes and I'm putting them into reaction types to simplify this mechanism. And another thing I did is everywhere that you see out, that just means we're leaving the isoprene mechanism and we're entering some sort of common organic species that you might see elsewhere. The reason I leave it out is just for visual clarity. And what you can see is that this graph is kind of neat and tidy. It's pretty easy to visualize and kind of see where things go. And I'm going to contrast that with a similarly small, even smaller mechanism that's actually a lot messier when it comes to graph theoretical representation. So this is a section of the NOx chemistry for geochem. And what you can see is that when trying to make a graph out of it, it's really messy. You can't use that trick I used where you take the background species and kind of typify them into the edges, because this is only background species. So we have 5 species and they're connected in this kind of crazy web of edges that are complex, because rather than connecting one species to one output, we're connecting, or one input species to one output species, we're connecting multiple reactants, multiple products. And the definition of an edge in this case gets a little murkier. And so what I'm going to do is just go through a few very simple graph examples and kind of show how they become graphs, simple mechanism, and show how they become graphs. And then kind of connect that to how easy it is to turn them into into some sort of algorithmic process. So one of the simplest forms of graph are trees, and in this case, a directed tree, wherein the edges have a direction, which corresponds to the direction of the reaction. So in this mechanism, we have two reactions, A going to B and A going to C. And each of those reactions can be represented by a single edge where A connects to B and A connects to C. A, B, and C are all nodes in this graph. And some characteristics of tree graphs: all nodes have one parent only, and no nodes are mutually reachable, meaning that there are no instances where B could reach C and C could reach B. So there's no reversible element to this. There's no cyclical element to it. It just goes in one direction. And all nodes have one parent. Now, a directed acyclic graph is a graph where we've eased up on one of those constraints. Now, all nodes can have more than one parent. So we have A goes to B, A goes to C, and now B goes to C. So if we look at C, C has two parents. Still relatively easy to represent this graph, or represent this mechanism as a graph. All we've done is add one edge connecting B to C. But we don't have the condition where all nodes have one parent. Now C has two parents. But still, no new nodes are mutually reachable. So none of these nodes can be reached by each other. So A cannot be reached by B, and well, A cannot be reached by B. B can be reached by A, but they can't both be reached by each other. Same goes for C for A and B, and obviously A for C. So then the next type of graph is a directed cyclic graph. Now nodes can be mutually reachable, meaning that you might have two nodes that can reach each other. So in this mechanism, we have A goes to B, A goes to C, but now C and B have this reversible reaction between each other. And that means they can reach each other. So you can go from B to C and you can go from C to B. And that adds a layer of complexity that makes certain things harder. It's easier to deal with a graph where nothing is mutually reachable than it is to deal with this kind of cyclic graph. And then finally, the directed hypergraph. Edges connect groups of nodes to groups of nodes. And that's kind of the most complicated iteration. And this is, the one that's most amenable to any type of mechanism, but it's also the least easy to put into some sort of algorithm. So the mechanism example is A plus B goes to C, C plus B goes to A, C plus A goes to B. All these species are now mutually reachable, and they're also connected by what we call hyperedges, wherein there are multiple species connected to multiple species. In this case, they're all connected to just one species, but the point being that there's not more than one node on either side of the edge. And you can already visually see this is a bit messier, and that kind of extends to actually trying to apply this to any sort of algorithm, in my case for reduction purposes. So I'm going to talk about an algorithm that I use within my main goal of mechanism reduction, and talk about it through the lens of each of these types of graph, and show how it gets progressively harder to make this algorithm work. And the algorithm is a species yield simulator. And what it does is determines the amount of any species in the mechanism that is produced from the source species. For example, the amount of formaldehyde produced from isoprene oxidation. And it does this for a set of input conditions. So you set the inputs and it determines what output yield is. And this yield is a time independent quality. So it's assuming that all reactions proceed to their full extent. And unlike a concentration over time output, it's not inherently dynamic. It's and therefore it doesn't actually necessitate the solving of an ODE if we make some assumptions. And so the benefit of this algorithm is that we can very quickly determine what the yields of the mechanism are without ever touching an ODE, without needing multiple timestamps, you're basically reducing the overall number of calculations by however many timestamps you would normally use. And so that's the benefit of it, and I use that in my reduction method. But let me just show you how it works for different types of graph. So here's a simple tree graph, and I'll just kind of demonstrate what I mean when I say like the yields. So here we're just going to assume that anytime there's a split in a species, so in this case A is split between B and C, we're just going to assume 50% of the moles of A go to B and C, and that will extend to the next species. So we start with 1 mole of A, we get a half mole of B, a half mole of C. That C reacts fully to form F, so we have a half mole of F, and we have a quarter of both D and E, because again, they're split evenly. And this, in essence, is what this algorithm does. It just distributes, I call it flux through the mechanism. And the reason I call it flux is because it's not distributing mass, because mass can be gained or lost based on, things that are adding or subtracted from the species themselves. And moles are not conserved either, because sometimes you have species that split apart. So it's not quite obvious what to describe this conservation as, but it's not moles and it's not mass, but it's something. Shindan, you have a question?
Yes. In some case, how do you deal with the cases when like A produce 2C?
Yeah, so that would be you would have A produces 2C, so A is 1, so it would be 2C. I guess it depends how we're doing the splitting, but if we're saying that for every A, 2C is produced, like even with including B, then we would get 2 for this, and then that 2 would carry over to the F. So these totals don't have to add up to anything, because nothing is inherently conserved. It's just saying how much of C is produced from A, if that makes sense.
Yeah, I'm just thinking like the edge represent the reactions, right? And the nodes represent the species. So if A produce 2C, where does this 2 is stored, and how does it convey through this network?
Yes, that's a good question. So I guess you could do it in 2 ways. You can add sort of a multiplier to an edge, or what I do usually is I use this as a representation, this graph as a representation, but then when I go back to distribute flux, I will connect back to those reaction stoichiometric coefficients as a multiplier. So you're never abandoning the reactions, you're just manipulating the graph, but then going back to the reactions for information. So there's always a mapping between the graph and the reactions. It's just, this is sort of how I like to conceptualize it and think about it. Yeah, but I don't, the 2C is not necessarily like stored in the graph itself, because inherently graphs contain usually less information than the mechanism, unless they are hypergraphs. And even then, stoichiometric coefficients have to do this add on. So if we're applying this algorithm to different types of graph, we can look at the difficulties involved. So tree graph, the yield comes from just one parent. Pretty straightforward to distribute yields, as we saw in this example. it's really the simplest application of this algorithm. The directed acyclic graph yield comes from multiple parents. It's not really a problem. It's just something to take into account, that the flux into C will come from both A and from B via the two-step process of A going to B and C. And you just have to take that into account. There's nothing inherently difficult about it. Daniel.
Yeah, thanks. I was just wondering if it's common practice or useful at all to transform a directed acyclic graph into a tree graph by like doubling up on a repeated node. So like
That's a
for
good
this
question.
one, you could have two C's.
That's a good question. So it would be helpful in diagnosing, let's say, where the C is coming from. So if you split up C as many times as it appears as a child, what you end up with is a diagnostic of this much C came from this pathway, this much C came from this pathway, etc. But then in order to actually know how much total C is produced, you end up recombining it. I guess it depends on the application. Both have uses, but maintaining the sort of true graph structure is useful when you're just counting the totals.
Gotcha. Thanks.
So now we come to the directed cyclic graph, and there we have a problem. So you can imagine we start with A and we go to B and C. The yields from B and C are kind of weird because they like from B it will go to C, and then C it'll go back to B. And it'll just bounce back and forth. And in this specific graph that I've drawn, it'll actually just be infinity, because if you're just counting how much flux is through these two species, there's no outlet and they bounce back and forth from each other. It's just gonna keep tallying and tallying and tallying. So that infinite number is not really a useful number. And so what I've done is, try to take a step back and just say, well, what is the useful number? The useful number is not how much bouncing back and forth you get within the cycle, but what happens once the species leave the cycle. And so let's say there was an outlet, both from B and C. How do we know how much is outlet from the B side and how much from the C side? And that requires its own special sub-algorithm to measure the output from a cycle. But it does work, and it is, highly accurate and deterministic. And given a set of inputs, you can find the outputs from that cyclic section of the graph. And then we come to the directed hypergraph, where you have multiple reactants and multiple products, but really multiple reactants are the difficult thing, because as y'all know, the reaction rate depends on the concentration of both reactants. And in a standard ODE simulation, these reactants can vary with time. And inherently in this algorithm, we're not varying anything with time. So what's the right value for these concentrations of these species? The answer is kind of hard to know what the right value is, and I don't know that this algorithm extends to multiple species reactants. Multiple reactant reactions and mechanisms. But I have started the process of trying to figure out what it might look like. And basically there are rules that you use based on the rate constants to kind of determine what the modified reaction rate should be, given that you have two species whose concentrations are varying over time, but they're reacting with each other. So what I've found so far is it's possible to begin to model this, but it's still very hard, and I don't know if it'll ever be fruitful. But in any event, the directed hypergraph is the most complicated and most widely applicable type of graph, but it is definitely not the only useful type of graph. So the criteria for the existing working rapid yield algorithm that I've worked on is the mechanism starts with a source species, which is only consumed, it's not produced, at least within the confines of the mechanism. The mechanism contains primarily forward moving reactions with some reversible reactions in the mix, but not dominated by them. And for any reaction with two reactants, there must be one reactant that can be taken as a constant for the purpose of the algorithm. And as it turns out, the isoprene mechanism, as with most organic mechanisms, kind of meets this description, at least for my purposes. So we have this, for example, isoprene is the source species that is only consumed. The mechanism does have some reversible reactions, but there's not a lot of them. They probably make up about 5% of the total reactions. And so it's dominated by just unidirectional reactions moving towards a more oxidized state. And for any reaction with two reactants, there must be one reactant that we can kind of assume is a constant. And that is a good description of most of the secondary reactants, which are NOx, OH, HO2, ozone. The less easy to model as constant ones would be like the organic radicals. And when I say that these are constant, I mean for a given run. You still might care about different concentrations of these species, but you're just assuming for your yield calculation that they're constant. And then if you want to know for different values, you have to do another yield calculation. But I think that's a suitable criteria for these types of species where, yes, they're influenced by the isoprene mechanism, but they're also very heavily influenced by external factors. And so taking them as constant for a moment in time is not the worst thing. So I'm going to go in a little more depth about how this algorithm works, especially with regards to cycles, because that's sort of the edge case that is definitely necessary when you're dealing with any sort of organic oxidation mechanism. So you're going to start with the initial concentration of the main species. We're just going to set it equal to 1. Distribute the mass in the mechanism by assuming all reactions go to completion. And the yield is the total amount of produced as a fraction of the initial isoprene amount. So that yield can actually be more than 1, as we talked about, but it's related to per mole of isoprene, how many moles of X do we get? And I've drawn this animation. Again, we're assuming it splits evenly. Pretty straightforward in this case. What about a cycle? Here I'm getting rid of the numbers and the names, just kind of focusing on the visual. So we have this cycle that's going between the source species of this subset and these two lower species. And what's going to happen is they're going to go to this lower species. And so now we have this issue of what happens now. Because it's this yield, this mass is going in both directions. It's going back up to the original source species and down to these other species. So how do you deal with that? So we're gonna put a box around our cycle and just look at it as this kind of object. And then anything that comes into it will be dealt with within the object. And then we're just looking at what comes out of it. What are the products? So we set the initial concentrations for the species in the cycle, assume that, and we set new concentrations, assuming all reactions go to completion, and iterate until we reach a steady state. So we're going to start with 1 there and go from there. So at 0 iterations, we've got 1 at the top. Now we've split it between the bottom 2. Now we've gone half to the top, half to the outlet species. 3 iterations, got now a half in the middle species, a half in the bottom, et cetera, et cetera. What you'll notice is that even after 6 iterations, there's still some fraction of the flux that's stuck in this cycle that hasn't made it out of the cycle. And that's kind of a problem because it could take infinite generations or iterations to actually get all that mass out of the cycle. And in some cases, where the cycle really rapidly is bouncing back and forth, that is a major problem because you don't want to do infinite iterations of this little back and forth thing. But you don't need to. What happens is, if you plot the concentration of the products over the number of iterations, you see that there's a plateau, and inherently that plateau should be predictable because it's deterministic. It's relying on the rate constants and the output. So this should be able to be figured out, and it's just a question of how. And actually, the data that we acquire from doing a few iterations is enough to figure it out. So if we plot the concentration of a given product on the y-axis versus the concentration of species within the cycle for a given iteration, what we get is this linear plot. It's just a purely linear trend line, because over time, as mass leaves the cycle, it leaves it in a linear fashion where basically, because the mass is conserved, we can just follow the trend line and predict what the product concentration will be when the cycle concentration is 0. So this data point where it's 0, 1, which represents 0 mass in the cycle and 1 mass out of the cycle, that's infinity iterations. But we don't need infinity iterations when we could just look at, let's say, the first data point and the second data point and follow the linear trend to infer the final data point. So with that, rather than doing, tons of iterations, we can set a first data point and a second data point of iterations for the cycle, and just extrapolate the data to find what the final product concentration should be. In practice, I do 20 iterations total. So for any given cycle, once I encounter it in the mechanism, I do 20 iterations of it. I take the concentration of within the cycle and outside of the cycle at 10 and 20 iterations to extrapolate what the product concentration will be once the cycle has fully, once everything has left the cycle. And with that, oh, yes, Danny.
Yeah, maybe an obvious question, but why do you do 20? I mean, couldn't you just do 2 or 3? Or is
That's
it
a good
always
question.
linear? Yeah.
So it's approximately linear in the sense that at really low iterations, it doesn't quite pan out. So if you can imagine, if we took at 0 iterations and 1 iteration, that's not going to do anything because we don't even have any concentrations within our product species. You have to wait until you get past a certain threshold where the cycle has, enough, you've run through the cycle of enough times that the linear extrapolation makes sense. And so, yes.
So just going off kind of Danny's question, just think, so you need to have this iterative cycling to flush out the species that are due to the bimolecular or the reversible reactions, is that right? Otherwise it would just be a one shot. And so these iterations are not necessarily time steps, it's just trying to get the stability of that final product, is that right? So this could be
exactly
1 time step, this could be 30 time steps. It's not it's agnostic to what your parent model is.
That's exactly right. It's the time steps are not it's not really time steps, it's really just like model steps, because time doesn't even play a role in this method, and the number of iterations you do will scale with the size of the cycle. So a small cycle like this one doesn't need 20 iterations. A large cycle will, and in the isoprene, I'm calibrating my number of iterations mostly to the isoprene mechanism, which has a cycle of containing 7 species in sort of a reversible reaction chain. It's not a perfect like unidirectional chain, but there's 7 species tied together. And that's what I'm calibrating it to. But I can imagine if for some reason you had like a 30 species cycle, 20 iterations probably wouldn't be enough. You might have to do more. And in terms of how much time these things take, or how much real time is passing, it's hard to even quantify. We're assuming all these reactions go to their full extent, which for some reactions takes a long time and for others does not. So it just depends. So this is just kind of a summary of that cycle description. And then here's some results, and it's actually gotten a little better since this plot, but I'm just plotting species yields measured in a box model versus species yields measured by the algorithm, and including oxidants and nitrogen oxide. So I have a process for tallying how much of those are produced or consumed. And it's pretty much right on the mark. There's a few species at lower concentrations that don't do well, and that comes into play, and that's when these multiple reactions come into play, where you have these isoprene like radicals reacting with each other, and that sort of throws a wrench into this method. But it's a small enough contribution that it doesn't matter a ton when I'm doing reductions. So that's the sub-algorithm for estimating yields, and it's a direct application of graph theory and kind of graph theory thinking in terms of what makes what types of mechanisms are applicable, which are not. So you can see here, there's this one species with relatively low yield that is off the line. That's one of those species that's heavily influenced by these isoprene radical on radical reactions. This runtime comparison is, I would say, underestimates the amount of time savings you're going to get from this by a fair amount. I haven't like optimized the algorithm yet. And I think even since I got this measurement, it's gotten faster. But it's about 3 times faster than my foam model right now. It's probably actually more like 10 times faster right now. It's definitely faster. I could not give you a really reliable number on how much faster it is to calculate the yields versus measuring them in a box model, but I know that it is definitely faster. All right, so then how this applies to an actual reduction algorithm. We take the inputs for every background species, so OH, HO2, NOx, organic radicals, ozone. Calculate the yields from the root species of all removable species from low to high, sorted from low to high. So that's where that algorithm I described comes in, where we're calculating the yields. And then the actual reduction is kind of simple. We remove species in order of lowest to highest yields. And all the products of the removed species are added to the products of the species that produce it. And I'll note here, it's kind of a relatively simple method of reduction. There are more complex or smart potential avenues for reducing, but it all rests on the backbone of which species are and are not important, and that comes from this yield calculation. So the key here is the ability to calculate yields, and then the reduction itself is, we can expand on that. And then the reduced output mechanism is with a number of species equal to the total minus the number that we removed in step 2. Here's a simple example. We have isoprene reacts with OH to form isop A. Isop A forms 0.8 isop B plus 0.2 OH plus formaldehyde. We remove isop A and we just stick the products, second reaction on the first reaction. So that's what it looks like from a sort of logistical perspective, but we're doing that with multiple species over multiple generations, sometimes condensing lots of generations at once. So here's some box model results with the number of species in the legend that are removed. So starting with 0 and going to 241 removed out of about 400. Not a lot of difference in isoprene because the algorithm isn't really touching isoprene that much because it shouldn't. So that's good. Formaldehyde, which is pretty much an end product, something that this yield calculation algorithm would want to get right, because it's being produced on many generations and at the end of many processes as well. And that's stayed pretty true to the original model for several levels of reduction, and same for this long named species, which is actually a subset of IEPOX. So we're getting pretty good fidelity with our reductions. Again, up to 240 removed out of 400 is like, what, 35% of the total, something like that. And more demonstrations with OH and HO2. You can see some discrepancies in NO2 and therefore ozone. Nothing crazy, but definitely noticeable, and usually scales with the amount of reduction. And then I have this amalgamated error metric, which averages over a few different conditions and a bunch of different species. And what you can see is that the error over the number of species removed is very low in the beginning and trends higher, which is something you'd want to have a well-behaved model. You don't want your error to suddenly jump up and be all over the place. You want to know that if you the more you remove, the more error you have, especially with lower error in the beginning. And then there's just a few different methods here. The baseline is when I'm just using my box model to calculate yields. The gray line is with the rapid yield algorithm, and then the orange line is implementing nitrogen conservation as well. All three of them do well. I would say a threshold of 1 is a goal for a highly reduced mechanism. I want to push that, the point where they cross the line, much further to the right, but this is still much better than other methods I've worked with before. And one thing to note is, like, once you get to really highly reduced, the error does kind of get a little unpredictable. So the rapid yield method, which trends worse for the most part, trends better at the end, which I don't have a good explanation for, except for things are just kind of getting wacky at that point. But overall, the method works well, and I'm hoping to get it to work a little better before I put out a paper with methodology and all that. But it's doing what I want it to so far. And just to highlight the importance of this rapid yield algorithm in actually contributing to the method, if we randomly order our species that we want to remove, you get the gray line, which is where, for any random ordering, you might strike gold and have a decent mechanism, or you might have something that looks pretty terrible. I haven't changed what I do once I pick which species to remove. I've just changed the order at which I've removed species. So clearly the order matters a lot. And unless you get to the very highly reduced end where it starts to not matter because they're all doing pretty poorly. So that is a highlight of the reduction method. And there's an example reaction from the actual isoprene mechanism, where this is a relatively early on reaction with this isop-1OH4 OOC with NO. And that's the initial set of products, and then the final set of products. And that's condensing a lot of chemistry down to this one reaction. And then just to kind of future thoughts, maybe there's a use for rapid yield algorithm in a 3D model where you don't necessarily care about the time dependence of, let's say, isoprene. You just want to know how much SOA is formed, because that might tend to linger. So I could imagine a world in where you incorporate this sort of a graph theory based yield algorithm into a 3D model for select subsets of your larger mechanism. And that might allow you to quickly do some calculations for like really quite large mechanisms that you would otherwise be prohibited from using because they're too big. Like if you wanted to model the specifics of alpha pinene, but you don't have the time to run an 800 species alpha pinene mechanism, but you might have the time to just quickly calculate the yields from alpha pinene. So that is everything. I will stop the share and I'm happy to take any questions. And I think I went a little over time. Sorry.